A supersonic electric aircraft priced at just $75,999 is rewriting the rules of aviation. Until now, the average cost of a 4- to 6-seat electric plane exceeded $1 million, but Tesla's new project, its super electric plane, has entered the scene as part of Elon Musk's next master plan. With the FAA recently loosening restrictions on private electric aircraft, Musk wasted no time, and today we are witnessing a triple breakthrough that is already being hailed as a turning point in aviation. Tesla has introduced a propulsion system with efficiency levels never seen before, adaptive wings that reshape themselves in flight for maximum performance, and a cockpit design so advanced that even veteran pilots are calling it the future of flying. This isn't just another news story, it marks the beginning of an entirely new era in transportation. Tesla's propulsion system represents the single biggest leap forward in aviation since the invention of the turbojet engine. Instead of relying on one or two massive power plants, Tesla employs a distributed propulsion array consisting of 23 lightweight electric motors spread across the wings and fuselage. Each motor weighs just 47 pounds yet generates 37 horsepower, giving the system a combined output of 847 horsepower and a power-to-weight ratio far superior to conventional piston engines. This distributed design not only increases performance but also ensures a level of redundancy no traditional aircraft can match. What truly sets the system apart, however, is its electromagnetic thrust vectoring technology, which allows thrust to be redirected in fractions of a second without relying on drag-inducing control surfaces. While traditional airplanes adjust direction through flaps, rudders, or elevators, Tesla's aircraft alters thrust itself, with response times as fast as 0.007 seconds. The result is precise maneuverability, including sustained vertical climbs and even zero-radius turns, flight dynamics that conventional aircraft simply cannot achieve. Tesla's adaptive energy distribution network further revolutionizes the power system. Monitoring motor performance more than 14,000 times per second, it redistributes load in real time depending on flight conditions. During takeoff and climb, power is concentrated on vertically oriented motors, while in cruise, the network optimizes output to minimize energy use. This dynamic system reduces consumption by 34% compared to fixed configurations. Even more impressive is the regenerative propulsion system, which recaptures energy during descent and landing. As the aircraft slows, the motors switch into generator mode, returning power to the batteries and recovering as much as 127 kilowatts, enough for 23 minutes of cruise flight. Together, these systems push efficiency into uncharted territory. Whereas combustion engines achieve barely 25% thermal efficiency, Tesla's system reaches 94% from battery to propeller. When regenerative braking and drag-free thrust vectoring are factored in, overall efficiency climbs above 100% during full flight cycles. This effectively means the plane creates more usable energy than it consumes, harvesting power from the very air it moves through. Such technology doesn't just compete with conventional engines, it makes them obsolete. But propulsion is only the first piece of the puzzle. Tesla has also transformed the way wings function. Traditional aircraft wings are fixed in place, which forces designers to compromise between lift, drag, and efficiency at different phases of flight. Tesla's adaptive wings eliminate those compromises entirely by using shape-morphing structures embedded with over 100 electromagnetic actuators. These actuators continuously adjust the camber, twist, and surface area of the wings in real time. During takeoff, the system increases wing camber to nearly 9 degrees and expands the surface area by more than 20%, producing far greater lift at lower speeds. This means the plane can lift off at just 47 knots, compared to 67 knots for conventional aircraft, cutting runway requirements nearly in half and opening thousands of smaller airports to Tesla aircraft that traditional planes cannot use. Once airborne, the wings automatically morph into a low-drag configuration, reducing drag by 64% during cruise. This improvement increases range dramatically and lowers energy consumption. The result is an aerodynamic efficiency ratio of 34:1, compared to 23:1 for fixed-wing aircraft. With over 1,800 carbon fiber segments and electromagnetic polymers allowing precise shape changes in as little as 0.012 seconds, Tesla's wings can adapt to turbulence faster than a pilot can react. Distributed pressure sensors detect subtle changes in airflow across the wing surface, and the system responds before the pilot even feels a bump. Flight in conditions that would ground ordinary planes becomes not only possible but routine. These wings are not merely an upgrade, they redefine what it means to fly. Inside the cockpit, Tesla has taken a bold step that combines artificial intelligence, human-machine interfaces, and even neuroscience. Instead of relying on mechanical controls or digital touchscreens, the new cockpit integrates directly with the pilot's nervous system through a non-invasive neural interface developed with Neuralink. This system interprets electrical signals from the pilot's brain and translates them into aircraft commands instantly, with zero latency. Traditional cockpit controls take nearly a quarter of a second for human input to translate into action, but Tesla's neural system operates in just 0.003 seconds, making the aircraft feel like an extension of the pilot's own body. Critical flight information is displayed not on panels but directly into the pilot's vision using augmented reality, overlaying speed, altitude, navigation, and traffic data seamlessly into the natural field of view. Pilots no longer need to look down or scan instruments, their awareness becomes total and uninterrupted. At the same time, a predictive AI assistant constantly monitors flight conditions, pilot biometrics, and system performance, anticipating the need for adjustments several seconds before the pilot consciously recognizes them. If turbulence is ahead, the AI prepositions the controls before the aircraft even feels the bump. Importantly, this assistance never removes pilot authority, it simply makes the pilot's actions smoother, safer, and more intuitive. Cognitive load management ensures safety by detecting fatigue, stress, or distraction in real time. When a pilot's attention wavers, routine tasks are quietly automated so the human can focus on decision-making. Emergency management reaches an entirely new level. The system can detect hazards nearly a minute earlier than conventional warning systems and guide the pilot with subtle neural feedback that feels like intuition rather than instruction. For the first time, the limits of human reaction time and situational awareness no longer define the boundaries of flight safety. Perhaps most ambitious of all is Tesla's atmospheric highway system, a reimagining of transportation infrastructure itself. Instead of relying on ground-based roads and highways, Tesla proposes a three-dimensional sky grid divided into altitude layers that extend from just above the ground to 18,000 feet. This creates 36 different traffic corridors where different classes of aircraft operate without interfering with one another. Personal aircraft might fly between 200 and 2,000 feet, commercial flights higher, and long-distance transport in the upper layers. Unlike traditional air traffic control, which depends on human operators and radio communication, Tesla's system is fully decentralized, with aircraft negotiating paths automatically through AI-driven communication protocols. Millions of possible routes are calculated per second, optimizing for speed, safety, and energy use simultaneously. If a storm disrupts part of the network, the system reroutes traffic instantly with no delays. The cost advantages are staggering. Building 1 mile of highway on the ground can cost over $4 million, not to mention land acquisition and environmental disruption. Tesla's atmospheric highways, by contrast, require only strategically placed charging stations every 67 miles. Outfitted with solar and wind energy systems, these installations feed directly into Tesla's supercharger network and cost less than $150,000 each. A fully connected network across the continental U.S. could be established for under $620 million, compared to trillions for equivalent road systems. For cities, this transformation is even more profound. With people traveling above the streets instead of on them, traffic congestion could drop by 2/3. Parking lots could vanish as aircraft are stored remotely and summoned on demand. Freed land could be repurposed for housing, green spaces, or businesses, reshaping urban life entirely. Remote regions, mountain towns, and isolated islands could be connected as easily as major metropolitan centers, dissolving the barriers that once limited economic growth. What this all adds up to is not just an aircraft, but a redefinition of what transportation can be. Affordable, zero-emission air travel no longer belongs to the realm of science fiction. The idea that taking off in your own plane could become as routine as driving to the grocery store is suddenly within reach. With Tesla's breakthroughs in propulsion, aerodynamics, human-machine integration, and infrastructure, we are witnessing the dawn of a new era. And remarkably, today's reveal is only the beginning.